The identities that we've introduced in Chapter 4 and the ones that we reviewed here in Chapter 5, of all of those, how many of them do you have memorized? You have all of them memorized, right? Darby, did you just put up 3 fingers? That's it? You only have 3 of them? Oh, you're talking about the Pythagorean theorem ones. But there's so many more, though, right? Yeah. I want you guys to know all of those. Yeah. But there are 3 main Pythagorean identities, so that's cool. And from those, we're going to develop even more. So let's go down here, and let's go ahead and look at, why would you do that? I want to verify the following identity. In other words, I want you to show me that the cotangent of negative x times the sine of x is in fact equal to a negative cosine of x. That's what I want you to do. Now, I can work on both sides of the equation simultaneously, right? No. I can cross the equal sign, right? I can move stuff from the right-hand side to the left and vice versa, right? No. Okay. No, because it's not an equation. It's an identity. I'm trying to say that whatever's on the left for any value of x will be equal to whatever's on the right for that same value of x. So use the identities that you know and show me that the left-hand side can be made to look like the right-hand side, or show me that the right-hand side can be made to look like the left-hand side, because that's really all we're doing. So try it. Let's see what you guys come up with. You already done? You think so? Let me see what you got, Lonzo. Sorry, dude. Awesome. Very nicely done. Good job. Just watching. Don't get nervous. Perfect. Good job. So what's the key to this one? The fact that this right here is what kind of function? It's an odd function, right? The cotangent of negative x is the same thing as the negative cotangent of positive x times sine of x equal to negative cosine of x. The negative cotangent of x can be rewritten as cosine of x over sine of x, still multiplied by sine of x, and that's equal to negative cosine of x. I now note that I can take this sine of x and divide with that sine of x, and we'll put a 1 there for both of them, which means that I have negative cosine of x, and I have just shown that it is in fact equal to negative cosine of x. In other words, I'm simplifying what's on the left so that it looks like what's on the right. Sometimes you need to complicate it. Could I have gone from negative cosine x up to cotangent negative x times sine of x? Yeah, I could have. It would have taken a little bit of thought and effort. You always want to start with the more complex side, if possible, and simplify it down. Starting from something that's simplified and making it more complex is difficult to do. Not impossible, but difficult. Okay? So, let's look at this next identity. I want to verify the identity. And I have sine of x minus sine of x cosine squared x is equal to sine cubed x. I want to verify. Now, there's a number of different things that I can do here. Okay? I want to do this as simple as possible, though. And honestly, it doesn't matter which side I start on. Because the left-hand side, while complex, is not any more complex than the right-hand side. But the easiest thing to do on this one is to start on the left-hand side and understand that this term has a sine x factor, and that term also has a sine x factor. And if I factor that out, I end up with sine of x times 1 minus cosine squared x. And that's equal to sine cubed x. Well, we all know what this is, right, Darby? What's it equal to? Sine squared, because it is an identity. It is a Pythagorean identity. And so now I have on the left-hand side sine x times sine squared x is equal to sine cubed x on the right. And since I have a single sine and I'm multiplying it by a sine squared, I add the exponents and I end up with sine cubed on the left-hand side. And on the right-hand side, I see, in fact, that it is sine cubed of x. Okay? Questions? Comments? These are kind of basic and kind of easy. Trust me, they get more difficult. This one doesn't necessarily have to be difficult, but when you first look at it, you've got 1 plus cosine theta over sine theta equals cosecant theta plus cotangent theta. I start on either left or the right. Which side do I want to start on? Joseph, which side do you want to start on? You want to start on the right. Okay, let's do that. Let's see what happens. Since you want to start on the right, what are you going to do? Dude, why did you say start on the right? Okay. All right, Troy, what do you think? At least you guys are being honest with me, and that's cool.
I'd start on the right. I have cotangent theta equals sine theta.
Okay, so we'll start on the right. Cotangent of theta. This right here, we're going to let that be cosine theta over sine theta. Okay? Plus, which means if I've started on the right, I got to look at cosecant of theta. What's cosecant of theta equal to? Okay, 1 over sine of theta. And I'm saying that that is equal to 1 plus cosine theta over sine theta. So how do I get these together? Well, common denominator, right? So that means that this simply becomes 1 plus cosine of theta over sine theta because of the common denominator, and I know that it is equal to 1 plus cosine theta over sine theta. And that's really all there is to it. Now, what if I started on the left-hand side? Could I still solve this or verify it? Sure, if I had started on the left-hand side, what would I do? Yes, Jesse? Okay, yeah, I would break it apart because I've got a 1 plus cosine theta over sine theta, which means that the sine theta is your common denominator. So I could have taken this whole thing and just rewritten it as 1 over sine theta plus cosine theta over sine theta. And I know that 1 over sine theta is going to give me cosecant theta. And then cosine theta over sine theta is cotangent theta. and I've done it. Now, which one was easier to do? 6 of one, half dozen of the other. This one took one less step, but it doesn't really matter. Actually, it didn't. It took the same number of steps. Doesn't matter. Okay, and sometimes you're going to work on the left for a little while, then you're going to stop, you're going to go to the right, work on the right for a little while. That's all you're doing with these. Do they get more complex? Yes. Why do I care about this? Because when I get into calculus, I'm going to need to use trigonometric identities to solve very complex integration problems. And that's why we spend an entire chapter on this stuff. And hopefully, you guys will know it really, really well by the time I'm done with you. And do not let you use a formula sheet. If you want to use a formula sheet, you should have taken somebody else. Okay? They are out there. We have instructors on this campus and on the Huntsville campus that let you guys use formula sheets. But by now you know I'm just not that nice. Okay? All right, let's do another one. Told you they get more complex. So, which side do we want to start on, Caitlin? Left or right? Okay. Now, let me ask you why you want to start on the left. And don't say because that's the one you think I should start on. I want you to tell me why you would start on the left versus starting on the right. Okay. The left side is way more complicated than the right side. It's going to be easier to simplify down the complex side than it is to take the simple side and make it more complex. There's a whole bunch of different things I can do here. So, let's think about it for a moment. What do you want to do? Which way do you want to go? Jesse?
Get them common denominators.
Yeah, find a common denominator between the two fractions. And what's the common denominator going to be? It's going to be this times that. And very simply stated, in order to do this, if I take this right here and multiply it by that right there, I'm going to get sine squared x. And then I've got this plus sign right here, and I'm going to put the plus sign right there. And then I'm going to take this right here and multiply it by this right here, which is simply going to give me 1 plus cosine x quantity squared. And we'll deal with that in a moment. And that's all going to be over 1 plus cosine x times sine x. Oops. That doesn't do me a whole lot of good, does it? Or does it? Well, we'll find out in a moment, shall we? What should I do at this point? It is one fraction. Okay, not distribute it, but, well, yeah, I guess it would be distribute, but we're going to use what method to assure that we get the right answer? Somebody. Darby, what are you going to do? Just go, stop calling on me. You would FOIL it. What's another method that I could use? I could do this. What's a plus b quantity squared equal to? A squared plus 2ab plus b squared, right? You guys all remember that? Right? Yeah. Okay, if you don't, FOIL it. So, and it's okay. So I've still got the sine squared x here. Okay. And I'm going to add to that 1 plus 2 cosine x plus cosine squared x. That's still going to be over 1 plus cosine x times sine x. And should I do anything with that? Should I multiply it together? What do you guys think? Yeah, this. Should I go ahead and distribute the sine x over the 1 and the cosine x? Good question, isn't it? What I'm going to suggest is that you don't at this point. Leave it alone. The reason being is because the numerator is still in a state of chaos, really. So let's go ahead and see what we can do with the numerator for a little bit, and then we'll deal with what's in the denominator, okay? What do you guys want to do with that numerator? Brat, what are you going to do? Where are you going to go? And if you don't know, just say, hey, I'm clueless at this point. It's okay, because trust me, you're not the only one. What are you going to do? Excellent. I notice that I've got a sine squared x here and a positive cosine squared x here. And if I add those together using one of my Pythagorean identities, that's equal to 1. So I'm going to have 1 plus, and I still have the 1 plus 2 cosine x here. And that's still over 1 plus cosine of x times the sine of x. And we're still saying that it's equal to 2 cosecant x. Let me draw another line there and hopefully make it. There we go. So, if I do 1 plus 1, I'm going to get 2, right? And I'll have 2 plus 2 cosine x in the numerator, which is going to be a really cool thing. Because if I look very carefully at this, I notice that I can factor out the 2. And I'm going to end up with a 1 plus cosine x, which will then divide out. Now, it's at this point that I'm going to say I'm going to pose the rhetorical question, do I need to show each and every step? No, you don't. However, do not go from what I give you and in the next step write 2 cosecant x equals 2 cosecant x without showing me anything. You laugh. A few of you are laughing. A couple of you are going, man, that's what I was going to do. Yes, I've had students do that, which is why in the directions of all my tests, I always write, show enough work to justify your answer. You got to show me at least 1 or 2 steps so that I know that you know what you're doing. And I'm kind of a stinker because while these say verify the identity, on the test, there will be a question that will not say verify the identity, but will say verify that this is an identity. Completely different type of problem, which means that you've got to show me that it is an identity or that it's not an identity. And if you do the whole just give me 1 step and say, yeah, it's an identity, then you might get it wrong, because if I say verify that it is an identity, it might not be. You've got to show enough work. And honestly, by writing out all the steps, it clarifies the process for you. Makes these things easier to do as you go along. Every math student hates the math teacher that requires that you show every single step. I did. I got in trouble in high school because I wouldn't, and then I would argue, or I'd do something completely different, and then I would argue, which is why I tend to write out in my directions, this is what I want you to do. The reason that math teachers want you to show the steps is because they want to make sure that you understand the entire process. That's why I do that. And by writing out all the steps, it clarifies the process for you. So now, at this point, I have 2 plus 2 cosine x over 1 plus cosine x quantity times sine of x. And I like the fact that the 2 and the 2 cosine x have a common factor of 2. So that's what we're going to do. We are going to factor out 2. And we will have 1 plus cosine of x. And that will all be over 1 plus cosine of x times sine of x. And I know that it is still equal to 2 cosecant of x. So, this whole term will divide with that whole term, right? Leaving me with a 1 and a 1. And now I'm left with 2 over sine of x. And I'm still saying that's equal to 2 cosecant of x. And I know that 2 over sine of x is going to be the same thing as 2 cosecant of x. And I have just verified the identity. All right, now I want you guys to try one. Verify the identity. Be recording this, right? Where was I? Negative sine x times 1. Plus, and then my last two terms is going to be negative sine x times sine x. And this is going to be 1. This is simply going to be plus sine x. This is going to be minus sine x. And this is going to be minus sine squared x, which gives me 1 minus sine squared x. So using the conjugate, that's what I end up with in the denominator. In the numerator, we'll stick with 1 minus sine x times cosine x. Okay? Let me get rid of this. So this whole thing now, when I rewrite it, I'm going to have 1 minus sine x times the cosine of x over 1 minus sine squared x. And that's still equal to whatever I've got over here, which is 1 minus sine x over cosine x. Now, what's 1 minus sine squared x equal to? Say what? Don't do that. Trust me. Let's just look at the denominator. What's 1 minus sine squared x equal to? Cosine squared x. And if I do that, if I leave the numerator alone, I've got the 1 minus sine x times the cosine of x, and I've just changed the denominator into cosine squared x because of the Pythagorean identity. I've got a single cosine x in the numerator, and I've got a cosine x squared in the denominator, which means that I can use a dividing out. It's still going to simply be equal to 1 minus sine of x over the cosine of x. So, this divides and becomes 1, and this divides and becomes cosine of x. Which means on the left-hand side, I now have 1 minus sine x over cosine of x, which just so happens to be exactly the same thing as what I have on the right-hand side. Principle of conjugates. I could do the same thing if I wanted to start on the right-hand side. Okay, if I look at this, I've got 1 minus sine x over cosine x. If I multiply the numerator by 1 plus sine x and the denominator by 1 plus sine x, the numerator is going to end up being 1 minus sine squared x, which is cosine squared x, over the denominator, which will be cosine x times 1 plus sine x. One of the cosines will cancel out, leaving me with cosine x over 1 plus sine x. In this case, it didn't matter which side I started on. But I still got to use that concept of conjugates. This right here is an incredibly useful technique. And you will use it a lot in Calculus 1 when you're dealing with limits and dealing with simplifying integrands in order to take and perform an integration. Questions? Yes, Jesse. Yeah, in my math lab, you got to love my math lab on these. You go, verify the following as an identity, and then it's like true or false. But you got to verify. You got to work through the problem. And also, if you want extra practice, just go to the textbook and look at the problems in each section. It is well worth your time and effort to do. Okay? So, let's look at this one. I like this one. Actually, you know what? We'll just do it like that. Okay. Verify that one for me. Tell me that the left is equal to the right. So what? What are you talking about? This one right here? You could do that. Try it. See what you end up with, bro. Tate, what are you doing? How are you addressing this problem? Or are you? Okay, talk to me about what your thought process is.
Basically, the denominator is 1 over cosine times 1 over sine, right?
Okay. Now, what does that really do for you guys? Because that's kind of where you were going too. And I want to ask you that question because there's something else that you can do that's actually a little easier to do. But what is your thought process? Where are you going to go with that? Okay. All right. Now, let me ask you this question because I would assume that a lot of you are actually thinking about that. What I see here, this part right here, okay, this to me looks like this, right? Some A plus B over C. And I don't care about the fact that the denominator has 2 factors in it. When I see a fraction that looks like that, one of the things that pops into my head is the fact that I can break it up into 2 fractions. A over C plus B over C. The reason that I'm thinking that for this one is I notice that there's secant in the denominator. And this is secant. So those could cancel, or I'm sorry, divide out if I broke it up as AC plus A over C plus B over C. Likewise, I've got a cosecant of negative x here, and in the denominator I've got a cosecant of x. But what do we know about the cosecant function? Is it even or odd? It's odd. Okay? And why is that important? Because what do I have over here on the right? I've got a negative sign. And since that's an odd function, I can move the negative sign out front. So let's do that. And what you guys were saying was not wrong. It's just going to be a whole lot more complicated to get where we're going. Okay? So I'm not trying to discourage you. I'm just trying to help you see these patterns that should eventually start to pop up on you. So I'm going to split this up into secant x over secant x cosecant x. And then I'm going to take this negative sign and bring it out in front and have a negative cosecant of x. I don't need that anymore. Over secant x cosecant of x. And I'm still saying that this thing somehow is going to be equal to sine x minus cosine x. Okay? All right, now, I know that this will divide with that, and what am I left with? Okay. And that's the reason I did it that way, because I have seen many students before do what I just did with the lines, divide them out, and then tell me it's equal to cosecant of x. But you got to remember that when you divide, you're replacing those numbers or those expressions with something else. They don't just disappear. And then I'm going to do the same thing over here. And so now I have minus 1 over secant of x. And yes, I'm pretty sure that that's still equal to sine x minus cosine of x. And now I can say 1 over cosecant of x, hey, that's sine of x. And I'm subtracting 1 over secant of x, which just so happens to be cosine of x. And that is, in fact, equal to sine of x minus cosine of x. Now, addressing what Abrat and Tate were saying is, yes, I could have changed the secant x, cosecant x into 1 over sine x cosine of x. But I'm still going to have to split things up and use my reciprocal identities, and it's actually going to become a lot more complicated. One of the things that I want you guys to get used to is when you're looking at these, anytime you've got a negative x, you should automatically be thinking, is that an even or an odd function? If it's even, just wipe that negative sign away. And what are the two even trigonometric functions? Cosine and secant. Okay? And if it's an odd function, move the negative sign out in front, because that will help you. Unless, of course, there's a negative value inside one of these, then you could leave it. But generally speaking, I'm trying to think, I don't think I've ever given you one like that before. Okay? Then once you do that, then be thinking about how you can split the fraction up. This right here is always best split into two separate fractions. The sum or the difference of two fractions. Okay? Any questions? We good? All right, here are your guidelines, and this is straight out of the textbook. And I've been saying this. You want to work independently on either side of the equation. It says work with each side of the equation independently of the other side. Start with the more complicated side and transform it in a step-by-step fashion until it looks exactly like the other side. You want to analyze the identity and look for opportunities to apply the fundamental identities, which is why I keep harping on, you guys got to know those. Okay, I'm not expecting you to remember or memorize anything like this, because that is an identity, but it's not what we consider a fundamental identity. And there's going to be some other identities that we're going to introduce in the next couple of sections that are going to expand how many fundamental identities we have. you want to try using one or more of the following techniques. You want to rewrite the more complicated side in sines and cosines, which is what you and Tate were trying to do, and there's nothing wrong with that. You want to factor out the greatest common factor. If you can get rid of the GCF, you're in good shape. Separate single term quotient into two terms, whether it's a plus or a minus, okay? I can combine fractional expressions using the least common denominator. I can multiply the numerator and denominator by a binomial factor that appears on the other side of the identity. So let's say that I had a sine x minus cosine x on the other side. I can multiply the left side by sine x minus cosine x over sine x minus cosine x. I wouldn't change the fundamental value, I'm just changing the way it looks. And don't be afraid to stop and start over again if you're not getting anywhere. That's going to happen. You guys are going to start cranking through the thing. All of a sudden you're going to be, wow, that's a dead end. I have no idea where to go. And then you're going to have to backtrack and start over again. It happens. It happens all the time. And I'll be up here doing some, and I'll think, oh, I know exactly what I'm going to do. And I start to try to disassemble it and simplify it, and then I end up stuck. Okay? It's like walking through a maze. Every now and then you're going to take a wrong turn. But what's the key to getting through a maze? Go ahead, Jesse. Keep your head. There's even better key. Take your left hand, put it on the wall to your left, and never let your hand leave that wall, and eventually you will find your way out of the maze. You guys ever been told that trick? Yeah. It may take you longer than some other methods, but I guarantee you're not going to end up in a dead-end situation because you're always going to keep walking. Even if you come to a dead-end situation, you're dragging your hand across the left-hand wall, you're going to finally get out. Why doesn't it work for the right hand? That's a question you guys should ponder over the weekend. You may see that again sometime. Okay. See, I always try to give you guys more information than what you expect. I have no idea. That's why I was asking the question. I want to know. And it doesn't. It does not. It doesn't work. Trust me. Always use your left hand. I know what you're saying, Jesse. It should work for the right hand. Okay. We can spend way too much time on it. Let's move on. You can think about it this weekend, Jesse. Who was it that came in late? Taylor, right? Okay, we're not meeting Thursday, okay. So, all right. I got a bunch of identities here, and I want to verify them. So I'm going to pick one. Let's look at number 46. Yeah. Let's verify. I got cosecant x minus cotangent x. Quantity squared is equal to 1 minus cosine x over 1 plus cosine x. So, say what? A minus b quantity squared is equal to what? There you go. Or just use the FOIL method. Now, why would we want to do that instead of break up the other one? Which one's the more complicated side, do you think? I'm thinking the left is more complicated. And it would be easier to make the left look like the right than the right look like the left. But let me say this. There are possibilities if I keep thinking about the different techniques that I have. I could use a conjugate. So let's you guys be working, see what you come up with. So who's got an answer for me? Okay, let's see. Let me pick on somebody else. Well, not pick. I mean, call on. Eric, what do you think? Still in? Okay. What do you got, Darby? Let me see what you did. Okay. Now, what I want you to do, though, is for the next step, is just go ahead and do the, yeah, okay, but that's perfect. Nicely done. Tevin, what do you got? Or do you? Still working? Let me see where you're at. Okay. All right. Now, is that going to help you, or is that going to make it more complicated? And it's okay if it's too complex and you got to back up and start over, or if you think that's going to work, just keep on going through it. Scott, what do you got? You done? Where are you at? Where are you at? That is the most ungrammatical thing I've ever said. Okay, so you want to try squaring this out, or do you want to multiply by conjugate over conjugate? Okay. So what are you going to do? I'm thinking multiply by a fraction that's equal to 1, right? And try 1 minus cosine x over 1 minus cosine x. And you came in late, so you're kind of lost, right? Okay. Now, yeah, okay, number one, that's not a bad idea to use these particular reciprocal identities or quotient identities. However, because you got this subtraction sign here, you can't divide across like that. Okay? So scratch and start over. Do you remember what a conjugate is?
I did in high school, but
Okay. What I'm going to suggest is multiplying the right-hand side by the conjugate of 1 plus cosine x, which is going to be 1 minus cosine x. And you're going to do it in the numerator and the denominator. And then just leave the left-hand side just like that, okay? All right. Troy, what do you got? Say what? Dead end, backing up? That's okay. Gentlemen, how we doing? Okay. What do you got, Tate?
Tried to do that one first and got stuck and started over on it.
Okay. All right. All right. So what I'm seeing here is good dedication to trying to work the problem. And some people started on the left, and there's nothing wrong with that. Some people started on the right, nothing wrong with that. It just depends on which side you think is the one that's going to be easier to transform into the other side. If you start on the left side, you're going to have to square this out, okay? And there's nothing wrong with that. But when I square the left-hand side out, I end up with cosecant squared x minus 2 cosecant x cotangent x and plus cotangent squared x. That's still got a whole lot of work to be done on. I got to be looking at the cosecant, which is 1 over the sine. I'm going to change the cosecant to 1 over sine here. Cotangent's going to be cosine over sine, and then this is going to be, well, cosine squared over sine squared. That one's really complex. And you could do it this way, but it's going to take a lot of work. Ideally, you want to start right here with, the conjugate of the denominator. I'm not saying that this is any more correct than squaring out the left-hand side. What I am saying is it's going to be easier to make look like the right-hand side. Now, remember what I said. You want to close these off in parentheses. That way you've got the product of two binomials in the numerator and in the denominator. In the numerator, I've got a minus b times a minus b. And I'm going to have to FOIL that out. Okay? Or I'm going to use a minus b quantity squared is equal to a squared minus 2ab plus b squared. However you want to do it. But this right here is going to be equal to 1 minus 2 cosine x plus cosine squared x. Okay? This denominator, which is really what I'm trying to get to, because now when I multiply the conjugates, if I have a plus b times a minus b, that's the same as a squared minus b squared. Simple. So this is my a, so that's going to be 1 squared, which I could write as 1 if I wanted to, and that's what I'm going to do. So that's going to be 1, and then I'm subtracting, and this is my b, cosine squared x. Now, why is that preferable to doing what I did on the other side? Because that's a simple Pythagorean identity. What is 1 minus cosine squared x equal to, Joseph?
I don't know.
Eric, what is it? Sine squared x, okay? So this is equal to, I still have the same thing in the numerator. But you know what? I probably didn't need to do that, but it's okay. We'll mess with it in a moment. I got sine squared x in the denominator. So what should I do? Split it up into what? 3 fractions, right? And don't forget that over here on the left-hand side, things are still the same. It hasn't changed, okay? And so we'll go down here and we'll split up the right-hand side and get 1 over sine squared x minus 2 cosine x over sine squared x plus cosine squared x over sine squared x. That's one thing I could do. There's actually a bunch of things I could do if I really wanted to. Okay? What does that do for me? Jesse?
Gives you cosecant squared x minus 2 cosecant cotangent x plus minus 2.
But this isn't squared, is it? It's okay. It's all right, though, because what we're going to do, and you're on the right track, is this. This one right here, yeah. Let's go ahead and change that into a cosecant squared x. And this one right here, that's going to be a cotangent squared x, right? And that's going to be a plus. Now let's look at the middle for just a moment. I can rewrite this as minus 2 cosine x over sine x times 1 over sine x, right? Actually, I want that backwards, sorry. Let's rewrite that. This is going to be 2 times 1 over sine x, and I still should make that separate, times cosine x over sine x. Now, why do I care? Well, what's 1 over sine x? Cosecant. What's cosine x over sine x? Cotangent x. And I think that's exactly where you were headed, Jesse, but it's okay. And what is that? A squared minus 2ab plus b squared, right? Which means I can factor this thing. And don't forget, one more. There we go. That means that if I go ahead and factor this on the right-hand side, it's going to be cosecant x minus cotangent x times cosecant x minus cotangent x, which is the same thing as saying cosecant x minus cotangent x quantity squared. There we go. And you could have simplified things differently and still come up with the same answer. Are these things easy to do? Sometimes yes, sometimes not so much. Are they quick? Sometimes yes, sometimes not so much. This one was not a quick and easy one. This one took a little bit of thought. These are like doing any other kind of puzzle. Whether you like to do jigsaw puzzles or you like to play video games that have puzzle modes in them, it's the same concept. You're taking what you know, you're applying logic to the problem, and you are unraveling it. That's really all there is to it. Okay? See you guys on Tuesday. Yes, Lonzo.